Hello everybody, uh, my name is Diazhan Uzbekov and today we will talk about 3D user interfaces. This is my presentation and this agenda, and I will start with introduction, and we will try to I will try to answer the question what are 3D user interfaces, and we will talk about application of 3D user interfaces such as video gaming, very large displays and mobile applications, and we will talk about technologies of 3D user interfaces as tracking systems and sensors, um, about to talk about other input devices, and we'll discuss about designing usable 3D user interfaces. Like many high-level descriptive terms in our field, such as virtual reality and multimedia, it's surprisingly difficult to give a precise definition of the term 3D user interface. Also, most practitioners and researchers would say, I know one when I see one, stating exactly what constitutes a 3D user interface and which interfaces should be included and excluded is tricky. The book 3D User Interfaces Theory and Practice. This book defines a 3D user interface as simply a user interface that involves 3D interaction. This is This simply delays the inevitable, as we now have to define 3D user interaction. Um, this book states that 3D interaction is the human-computer interaction in which the user's tasks are performed directly in a 3D spatial context. One key word in this definition is directly. There are some interactive computer systems that display a virtual 2D space, but the user only interacts indirectly with this space. For example, by manipulating 2D widgets, uh, entering coordinates, or choosing items from a menu. These are not 3D user interfaces. Okay, application of 3D user interfaces. Why is it important to understand and study 3D user interfaces? For many years, the primary application of 3D user interfaces was in high-end virtual reality and augmented reality systems, since users in these systems were generally standing up, walking around, and limited in their view of the real world. Traditional mouse and keyboard-based interaction was impractical. Such systems were already using spatial tracking of the users had the correct view of the virtual world. It was natural to also design user interfaces that took advantage of spatial tracking as well. As we indicated above, however, recent years have seen an explosion of spatial input in consumer-level systems such as game consoles and smartphones. Thus, the principle of good 3D user interfaces design are now more important to understand than ever. To further motivate the importance of 3D research, let's look in a bit more detail at some important technology areas where 3D user interfaces are making an impact on real-world application. We will start from video gaming. Uh, there are we talk about uh, the three video gaming that Nintendo Wii, Microsoft Kinect, and Sony Move. As we have already mentioned, most people today are aware of 3D user interfaces because of the great success of motion gaming systems like Nintendo and Kinect. Uh, all of these systems use special tracking to allow users to interact with games through pointing, gestures, and most importantly, natural movements rather than with buttons and joysticks. For example, in archery game, a user can hold devices, two tracked devices, one for the handle of the bow and the other for the arrow and string, and can pull back the arrow, aim and release using motions for very similar to archery in the real world. This is example of PlayStation 3 move. Okay, the YE and Move both use tracked handheld devices that also provide buttons and joysticks, while the Kinect tracks the user's body directly. There is a clear trade-off here. Um, Buttons and joysticks are still useful for discrete action like confirming a selection, firing a weapon, and changing the view. On the other hand, removing encumbrances from the user can make the experience seem even more natural. 3D user interfaces are great fit for video gaming because the emphasis is on a compelling experience which can be enhanced with natural action that make the player feel as if he is part of the action rather than just indirectly controlling the actions of a remote character. Okay. Now, what about the very large displays? Recent years have seen an explosion in the size, resolution, and ubiquity of displays. So-called display walls are found in shopping malls, conference rooms, and even people's homes. Many of these displays are passive, simply presenting canned information to viewers, but more and more of them are interactive. So how should one interact with these large displays? The traditional mouse and keyboard still work, but they difficult to use in this context because users want to move about in front of the display, and because such large displays invite multiple users. Touchscreens are another option, but that means that to interact with the display, one has to stand within arm's reach, limiting the amount of display that can be seen. 3D interaction is a natural choice for large display context. A tracked handheld device, the hand itself, of the whole body can be used as portable input that works from any location and makes sense for multiple users. The simplest example is distal pointing, where the users point directly at the location on the display, as with a laser pointer, to interact with it. But the other techniques, such as full-body gestures or viewpoint-dependent display, can also be used. This is an example of freehand pointing and clicking interaction with very large high-resolution displays from the distance.
We apply a low-pass filter to reduce this effect. Raycasting allows the user to quickly point to the far ends of the display, but tends to be inaccurate for small targets. The relative pointing technique is loosely based on the hand motion when operating a mouse. A closed fist clutch gesture allows the hand to disengage from the cursor to recalibrate the hand and pointer relationship. We show that the clutch is active by dangling the cursor. To help the user form distinct postures, we show a red disc which becomes more intense as the gesture becomes more ambiguous.
Okay. The next is mobile. The next are mobile applications. Today, mobile devices such as smartphones and tablets are an interaction designer's playground, not only because of their rich design space for multi-touch input, but also because these devices incorporate some fairly powerful sensors for 3D spatial input. Perhaps the most prominent example of mobile device 3D interaction is an mobile AR. Mm, the smartphone becomes a window uh, through which the user can see not only the real world but virtual objects and information as well. Thus, the user can browse information simply by moving the device to view a different part of the real world scene. Yes, mobile augmented reality is information simply by moving the device to view a different part of the real world scene. Mobile augmented reality is being used for applications in entertainment, navigation, social networking, tourism, and many more domains. Students can learn about the history of an area, friends can find restaurants surrounding them and link to reviews, and tourists can follow a virtual path to the nearest subway station. Prominent projects like MIT Sixth Sense and Google Glass uh, project have made mobile augmented reality highly visible. Good 3D user design is critical to realizing these visions. Um, Google Glass is a type of wearable technology with an optical head-mounted display. It was developed by Google with the mission of producing a mass-market ubiquitous computer. Google Glass displayed information in a smartphone-like hands-free format. Wearers communicate with the Internet via natural language voice commands. This MIT Sixth Sense is a gestural interface device comprising a neckborn pendant that contains both a data projector and camera. Head-worn versions were also built in MIT Media Lab in 1997 that combine cameras and illumination systems for interactive photographic art and also included gesture recognition, for example, finger tracking using color tape uh, on the fingers. Okay, as we discussed above, special tracking technologies are intimately connected to 3D user interfaces. In order to design usable 2D user interfaces, then a basic understanding of special tracking is necessary. In addition, other input technologies and display devices play a major role in 3D user design. Special tracking system sense this position, orientation, linear or angular velocity, uh, and or linear or angular acceleration of one or more objects. Traditionally, 3D user interfaces have been based on 6 degree of freedom 6 DoF position trackers, which detect the absolute 2D position, location in a fixed XYZ coordinate system, and orientation um, of object, which is typically mounted on the head or held in the hand. These 6 DoF position trackers can be based on many different technologies, such as those using in electromagnetic fields, uh, Polymus Liberty, for example, optical tracking, this is natural point OptiTrack, or Gibrid, ultrasonic inertial tracking, like Intersense is 900. All of these, however, share the limitation that some external fixed reference, such as base station, a camera array, a set of visible markers, or an emitter grid must be used. Because of this, absolute 6 DoF position tracking can typically only be done in prepared spaces. Uh, while special tracking is a fundamental input devices for 3D user interfaces, it is usually not sufficient on its own. As noted above, most handheld trackers include other sorts of input because it's difficult to map all interface actions to position, orientation, or motion of the tracker. For example, to confirm a selection action, a discrete event or command is needed, and a button is much more appropriate for this than a hand motion. The InterSense is 900 is typical of such handheld trackers. It includes four standard buttons, a trigger button, and a 2-DOF analog joystick, which is also a button, and handheld form factor. The Kinect, because of its controlless design, suffers from the lack of discrete input such as buttons. Hand gloves or finger trackers are another type of input device that is frequently combined with special trackers. Pinch gloves detect contact between the fingers, while data gloves and finger trackers measure joint angles of the fingers. Combining this with trackers allow for interesting, natural and expressive use of hand gestures, such as in air typing, writing or sign language input. Um, Designing usable 3D user interfaces. First, we know the design space of 3D interaction is very large due to the number of the devices and mappings available. Second, 3D interaction design can be magical, limited only by the designer's imagination. Third, new technologies such as the Leap Motion device with the potential for new forms of interaction are constantly appearing. For example, in a recent project in our lab, students used a combination of recent technologies, multi-touch tablet, 3D reconstruction, marker-based augmented reality tracking, and stretch sensors to enable augmented reality Angry Birds. A novel form This is a novel form of physical interaction with both real and virtual objects in augmented reality. Finally, techniques can be designed specifically for specialized tasks and in various application domains. We design domain-specific interaction techniques for object cloning in the architecture and construction domain. There are some suggestions. First is be careful with mappings and DOFs. One of the most common problems in 3D user design is the use of inappropriate mappings between input devices and action in the interface. The second is keep it simple. Also, 2D user interfaces can be very expressive and can support complex tasks. Not all tasks in a 3D user interface need to use fully general interaction techniques. When the user goal is simple, designers should provide simple and effortless techniques. And the next is design for the hardware. In traditional user interfaces, we usually try to design without regard for the display or the input device. Um, User interfaces should be just as usable no matter whether you are using a large monitor or small laptop with a mouse or trackpad. This is not always strictly true when you have a very large multi-monitor setup, for example. But in the 3D user interfaces that works on one display or with one device very rarely works exactly the same way on different systems. Uh, you may still have the trained users, but a little training can go a long way. And the finally, always evaluate. Um, fi- uh, the final suggestions is that all 3D user interface designs should undergo formative empirical usability evaluation with members of the target user population. While the guideline probably applies to all user interfaces, 3D user interfaces in particular are difficult to design well based on theory, principles, and intuition alone. Many usability problems don't become clear until users try the 3D user interfaces, evaluate early and often. Uh, we we don't know what the future holds for us. The future, or what kind of future we are preparing. But the world will change because already in the pipeline such interesting technology as, for example, large wall hung high definition color displays, video walls including living area use of virtual reality, electronic notebook, contrast paper even after power off, video playback over network at 10x normal speed, high quality A3 flat displays using digital paper, 3D video conferencing, etc. That's all. This was my presentation. Thank you for your attention.